Hello there. Welcome to Physics Chapter 5, Lecture 1. We are in the second quarter of this course. And the material continues to just get more and more interesting. In my opinion, what you're going to need is the Chapter 5 lecture notes, your book, turn to page 141, and we are going to also be using a calculator in this lecture. So, probably if you've had a science course before, especially like a physical science course in middle school, you talked about Newton's laws, okay? Isaac Newton, really the father of modern physics in a lot of ways. So Newton's first law is unless a force is applied, an object remains at rest or moves with constant velocity. Okay, so what we're talking about, maybe you've heard this term before, is inertia. So objects want to either stay at motion if they're in motion or remain at rest if they are not moving. So let's look at On Your Own 5.1. Says you've started your Christmas shopping early and are driving on a highway with several packages on the seat next to you. Suddenly, you're forced to accelerate quickly in order to avoid hitting a car that's getting on the highway from an entrance ramp. You notice that even though the road is level, the packages slide backwards in the seat until they hit the backrest. Why did the packages slide backwards when you accelerated forwards? All right, so the packages were moving just at a certain speed. All right, I don't know. Let's say they were moving at 30 miles an hour, okay? They want to continue moving at 30 miles an hour. However, you suddenly speed it up, okay? So they wanted to stay at the original speed. And they did that until a force was applied. That force was until they hit the backrest. Or the seat. The vertical part of the seat. When they hit that, a force was applied and it sped those packages up to whatever the car was going. All right, so pretty simple concept and something that you deal with in everyday life all the time. All right, 5.2. says we all know that if you slide a block of wood on ice, it will travel much farther than it does on concrete. Use the law of inertia and the concept of friction to explain this fact. All right, well, friction just opposes motion. We'll talk about that a lot in just a little bit. So it's an impediment to motion. All right, so ice has much less friction than concrete. It's much more slippery, right? So if you have less force opposing the motion, then that block of wood will go farther. All right. So moving on down your notes, let's talk about Newton's second law. It says the acceleration of an object is directly proportional to the magnitude of the imposed force. As force increases, acceleration increases. Now, Newton's second law can be summed up with one of the most famous equations in physics, maybe the most famous equation. And that equation, I've given you room on your notes to write it in. Got to memorize it. It's the sum of all the forces. Force is a vector, is equal to mass times acceleration. All right, so this would be force. This Greek capital sigma means to sum up or add up. M is mass, and of course acceleration we've used a lot already. All right, A for that. Okay, so we're going to be using this equation a great deal in Chapter 5 and Chapter 6. One of the most important equations in physics. So that's Newton's second law, just in a math equation. Newton's third law is if object A exerts a force on object B exerts a force on object A, equal in magnitude and opposite in direction to the force exerted on B. So equal in magnitude, opposite in direction. All right, so if we were doing this class in person, I would do some examples there, such as pushing on a wall. Instead, I'm just going to link some videos in the description box, so make sure you watch those videos that I find that just give a summary to Newton's three laws. All right, so friction, I said we were going to talk about that a little bit, and that's such an important concept in Chapter 5 and Chapter 6, is a force opposing motion due to surface contact. Friction acts parallel to the surface of contact. All right, so you've got a little space here. We're going to draw this illustration, the frictional force illustration. So let's say this is the floor and we have a box. We want to push a box along the floor. Let's say we're going to push it to the right. We'll use an arrow indicating we're pushing a force to the right. Now the frictional force acts at the surface of contact. It opposes motion, so opposite motion. In friction, we use a small f. All right, whereas normally with forces we use a big F. So our little f is equal to friction. So acts at the surface, and we use a little f. Now the units that we're going to use for force is the Newton. N is Newton. And the unit, that's it says on your notes, the SI, that's just a fancy System International is what that stands for. And it's just metric, it means metric. Now that, I've got a dash, that's not a minus sign there on the unit. It's kilograms times meters. So kilogram meter, I probably should have put a dot there. I probably couldn't find that when I typed it so many years ago. Over seconds squared. But any mass times distance over time squared is a force unit. So that's the one we're going to use the most, Newton. Now there's another one, a dyne. This is not nearly as important, but I think you need to know it for, a review question possibly. That is a gram centimeter per second squared, so just a smaller unit. All right, so the dyne, we're not going to use that much. Mostly use newtons with metric, and we'll use pounds in English. All right, let's take a look at, on your own, 5.3. Okay, so in the book we're moving over to page 148. It says a man is pushing a car that's run out of gas. If he pushes with a force of 15 newtons west, and the car has a mass of 1.23 times 10 to the 6 grams, what will be the car's acceleration? Well, if we're in newtons, we need to get that grams into kilograms. Remember, a newton the Newton unit is kilogram meters per second squared. So we're going to have to get grams to kilograms. So let's do that real quick. And you could probably just do this in your head, but I'll do the factor label method. That's 1.23 times 10 to the 6 grams. Put that over 1. We want to change that to kilograms. Get rid of grams. One goes by the bigger one. Kilograms are bigger than grams, so one goes by the bigger one. There's 1,000 grams in a kilogram. So you would just divide that number by 1,000. That's 1.23 times 10 to the third kilograms. And if you don't want to use scientific notation, just 1,230 kilograms. All right, so we want to know what's the car's acceleration. Well, we know that force, we just have one force here, so I'm not going to have to sum them up, is equal to mass times acceleration. Therefore, if we solve for acceleration, that's going to be force divided by mass. All right, our force is 15 newtons. Mass is 1,230 kilograms. So that's going to be 0.012 meters per second squared, and since it's a vector, we need to write that is west. All right, so our first use of F equals ma. All right, 5.4. Let's read through this, not a math problem. It says a tennis ball bounces as shown in the diagram on the right. How can you tell that a force other than gravity must have acted on the tennis ball? Well, it's not moving down, is it? The ball is moving up, so gravity just causes things to move down. So part A would be it's moving up. All right, part B of this question is, at what point did the force act on the ball? Well, at the floor, or the ground. That's where it changed directions, didn't it? So that's where the force acted. All right, part C. What is the general direction, up, down, right, or left, of that force? Well, the general direction would be up and a bit to the right. So I'm going to write up and right, because it's not just straight up, is it? And then part D says, what's the general direction, up, down, right, or left, of the acceleration resulting from that force? Well, it's in the same direction as the force, up and to the right. All right, so 5.4, it's not meant to be difficult, just kind of common sense answers on that. All right, well, flip your notes over to page 2, and I'll clean off our board. And we'll do the second half of today's lecture. All right, the difference between weight and mass. All right, so in chemistry class, if you had me for chemistry, we kind of didn't really differentiate between weight and mass. But there is a difference. It's a big difference. Weight is the force caused by gravity. Okay, force caused by gravity. So our equation for weight equals mass times gravity. Okay, so you've got to memorize that. The units are newtons, if you're metric, or pounds, if you're English. Okay, newtons or pounds. So what is mass if it's different than weight? Well, mass is the quantity of matter in an object, and mass, this is the key, mass is the same everywhere. It doesn't matter what the gravitational acceleration is. Your mass is the same as on Earth, as it is on the moon, as it is on Neptune. So to get mass, we just rearrange this equation and solve for mass. Mass is equal to weight divided by gravity. All right, mass units are kilograms if you're metric, or this is one that I introduced you to actually in chemistry, slugs if you're in English. All right, kilograms or slugs. We mostly use metric, but we do a little bit in English. All right, let's look at 5.5. So you'll need to flip over to page 152. It's page 152. It says, what is the weight of a 13.5 gram object? We need to give our answer in newtons. Okay, well first we need to change 13.5 grams to kilograms. So I'm not going to go through the factor label method here. I just want you to kind of know 13.5 grams. You'd need to divide that by 1,000, so that's 0.0135 kilograms. I kind of want you to get to where these simple conversions, you're not having to do the factor label method. So divide by 1,000, that's how many kilograms, 1,000 grams in a kilogram. All right, so weight is equal to mass times gravity. So our mass is 0.0135 kilograms. Well, what's the gravitational acceleration on the Earth? Well, been using that a lot, 9.8 meters per second squared. And you'll end up getting your Newton. You know you've done it right because it's going to be kilograms times meters per second squared, which is a Newton. Right? If you put that in your calculator, you get 0.13 newtons. All right, right underneath that, 5.6 says a Martian rock weighs 15 newtons on Mars. How much will it weigh on Earth? And the acceleration due to gravity on Mars is 3.7 meters per second squared. So Mars actually is less than half the size of Earth. People think it's kind of a sister planet. It's really not. Venus is more of a sister planet to Earth in terms of size than Mars. Mars is closer, honestly, to the size of the moon than the Earth, or right in between anyway. All right. So 5.6 says rock weighs 15 newtons on Mars. So we need to get the mass, because the mass is the same everywhere. It's weight divided by gravity. The weight is 15 newtons. Gravity on Mars is 3.7 meters per second squared. All right, and that is 4.05 kilograms. Now that's the mass. The mass is the same everywhere. So to get the weight on the Earth, it's mass times gravity, but we're going to use Earth's gravity. So that's 4.05 kilograms times 9.8 meters per second squared. That's 39.7 newtons. So you can see on the Earth it weighs more than twice as much as something on Mars. All right. So our last concept on the notes is called the normal force. So this is just the last concept for today's lecture, the normal force. The component of force that acts perpendicular to the surface of contact. Okay, so in this chapter we're not going to use any angles. We'll do that in chapter 6. But I want to just go ahead, let me go ahead and erase this, and we'll draw out the normal force illustration. So let's go ahead and use our box. And box is on the ground here. The weight of the box, if it's not on an angle, acts straight down. That's the weight. The normal force acts opposite. All right. So perpendicular to the surface of contact. We call the normal force F sub n. Now normal force is what we use to calculate friction. Right? This is called a force diagram. You also might see it called a free body diagram in engineering school. Some old school professors may call it a free body diagram. Okay, so a force diagram. So the normal force is just equal to the weight in all Chapter 5 problems. That's because there's no angle in Chapter 5. In Chapter 6, that's not true. We have to use trigonometry. So that's because it's on a flat surface. Okay, so you have some space in your notes to do that. So let's look at on your own 5.7, and that will finish up lecture number 1 for Chapter 5. All right, so we are on page 154 here, right at the bottom. It says a 3.8 slug woman stands on a step. What is the normal force exerted by the step? So again, in this chapter, the normal force is just equal to the weight. That's because there's no angle. All right, you're not standing at an angle. It's just a flat horizontal surface. Okay, so we need to figure out the weight of the woman. Weight is equal to mass times gravity. We've already said in the problem that the woman has a mass of 3.8 slugs. So what's gravity? Is it 9.8? No, we're in English, so it's 32 feet per second squared. All right, so the woman weighs 121.6, and what do you think the force unit is? Weight is just a force. Is it newtons? No, we're in the English system here, so it's pounds, what you're used to. That woman weighs 121.6 pounds. All right, that does it for lecture number 1 in Chapter 5. You can do an awful lot of the problems, so the homework, voice just cracked, no idea why. The homework problems are review questions, page 174, 1 through 8, and you can do the practice problems on page 175, 1 through 6. All right, pretty easy problems math-wise. Just make sure to watch those videos. I link in the description box, and I will talk to you on lecture number 2.